This is Eric Linwood back with you with more self-elevated EDF/spring powered universal exoskeleton armor updates. And I basically, this is a rough blueprint I designed to have one single electrical motor represented right here, control a whole leg, three different points, being the knee, the hip up here, and then down to the ankle. And basically what I did is I took a motor and spin it up to whatever RPM I wanted to do. It's a dual shaft motor, shaft on each end, with a 4-gear transfer. And what that 4-gear transfer on each end does is it's got 1, 2, 3, 4 shafts. Now those 4 shafts are continuously turning, and when you turn the motor on, all 4 of those shafts are turning. This shaft is turning clockwise. This shaft is turning counterclockwise, clockwise, counterclockwise. Okay. Now what I did is, instead of having the motor directly drive a gear reduction to the output shaft on the hip, and the gear reduction I'm using, once it stopped moving, once you stop putting mechanical energy into it, or revolutionary energy to it, or rotating energy, whatever you want to say, it actually locks up and stops. And that's good for orthopedic and different applications for it when you're not putting power to the exoskeleton and holding them in position without using power, but still add actuation. Right, okay. Now what I did is, like I said, instead of linking this motor directly to that unit, I put it through gears, 2 counter-rotating shafts hooked to magnetic clutches. These magnetic clutches only engages the shaft when electric current is put to it. That way, this counterclockwise can turn the shaft one way. It just transfers energy up to the next casing. There's 2 casings. Transfers it up to here, and it basically, when you engage that magnetic clutch, it turns it. When you disengage it, it lets it go and it locks up. Same thing here on the other side, but it's spinning in the opposite direction. Engage the magnetic clutch, it turns the shaft, let go of the magnetic clutch, and the shaft locks up at the hip joint, and that's what's going to give you your backwards forward motion, engaging the counterclockwise and the counterclockwise magnetic clutches, engaging the gear that turns this shaft, engaging the bigger gear that turns the output shaft. And like I said, the whole time, this electric motor is going to be turning this shaft, this shaft, this shaft, and this shaft the whole time. And it's only going to be interacting with the output shafts when the magnetic clutches engage. Counterclockwise, right here, clockwise right there, and that's what's going to allow it to go forward and backwards without stopping the motor and putting reverse current into the motor. See, with a conventional, that motor is hooked directly to the output shaft. What that does is, when it's going one direction, the motor literally has to stop and then turn back on, putting reverse polarity or reverse current to the motor to get it the other way. Well, when you do that real quick, you overheat the motor and burn the motor up. That's what limits its speed. But when you do it the way I'm doing it, the motor stays on. It's always spinning. It's just like a lawnmower or a clutch on an AC. When you engage the belt on it, or on a helicopter or something of that nature that has a clutching mechanism, and it only engages the shaft when the magnetic clutch. That allows you not only to engage it forward or backwards whenever you want to, like I said, turn that motor the same way. It also keeps that motor spooled up at a RPM, a faster RPM, so it won't have to go to 0 to 100. It's already at 100, so it don't have that delay of the motor spooling up to react to that gearbox and that output shaft either. So it's gonna make that motion quicker because the motor's already spooled up. Instead of you engaging it, the electrical current to the motor, then it's spooling up and turning it, you're just engaging the magnetic clutch and it's immediately grabbing it and it's spinning whatever RPM that motor's spinning through that gearbox. So that's the difference. And like I said, I linked the cabling system here to control the ankle, and I put that third locking output gear right there, and that's controlled by a cabling system that runs down either side of the leg unit on the thigh area down to the calf through that cabling system linked to the ankle to give your ankle up and down motion so you can push off with your foot. And like I said, this is the fixed gear setup right here, output shaft for the knee, and that one up there for the hip. But it's Eric Linwood, and I'll be back with you with more self-elevated updates and see if I can develop this blueprints and prototype even further.